Last week we started to talk about interprocess communication, um, or how to use shared memory or pass message between processes. So we're going to go through this in a lot more detail today and walk through some code examples of how you do this in practice. To refresh on the idea, the problem is, imagine you had a location in memory and two processors wanting to read it. So the idea would be this first CPU reads a memory location. So say it read the value in as equal to 0. It wanted to do some work. It wanted to increment it and then write it back. So at this point, then you'd update your memory to have the value 1. Then this second CPU would come in and read this memory value. It would read in a value 1. Say it wanted to decrement, you'd write back to give a value of 0. That's all straightforward. This would work fine. The problem is what happens if the first CPU read a value of 0, and the second CPU read a value of 0, and this one incremented it, wrote back a value of 1, and then the second one decremented it and wrote back a value of -1. Then what's going to be in this memory location, whereas you want it to be a value of 0, it's actually going to store a -1 because it's the last thing that's written. Or in other words, what's performed by CPU 1 has just been completely lost because it wrote something and then it was immediately overwritten. So how can you get around this? One idea is to use a flag. So you could say, well, you can only read or write or access this memory location if you hold the flag. So how do I create a flag? Well, I create a flag. This can be my location in memory which has a flag. And so I can only use the memory location in red if I hold the flag. So let's initialize the flag to 0. What do? CPU 1 grabs the flag and then changes it, says, okay, it's going to be a 1. Then it reads from memory. CPU tries to read from memory, but it can't because the flag is a 1. It sees a 1, so it says wait. CPU 2 finishes its memory work. Then it updates the flag to be a 0 again. And you can imagine this would all work beautifully, but there's obviously a problem, and that is the exact same one as before. So I've got my flag. What happens? So CPU 1 checks the flag, it has a value of 0. CPU 2 checks the flag, it has a value of 0. CPU 1 changes the flag to 1. CPU 1 reads from memory, CPU 2 reads from memory, CPU 1 writes to memory, CPU 2 writes to memory. So you've got the exact same problem and haven't solved anything with the use of a flag. Right. So this is what is highlighted if you wanted to walk through it in your own time. First CPU sees a flag, second CPU sees a flag. First CPU says, I've changed the flag to 1, I'm going to use the write to the memory location. CPU 2 says, well, I can access the memory location and overwrites the data. So what you need is some kind of operation to avoid this problem. This is where atomic test and set comes in. So this is not nuclear. This is just saying it's a single operation. You can't break up the atom. So it's as small an operation as you can have. And the point is, it's a single bus operation which reads the memory location, tests it, and writes it. So in other words, it tests that my flag is 0, and if it is a 0, you can write it to a 1, all within one operation, so another processor can't take over and read the same data. So this is something that a lot of processors will support. So the w9l 2 has the ability to do test and set if you set this up. Here's an example of how you would do it in ARM. So let's just draw a picture. Imagine I had some memory. This is my memory. With my writing you can't read. And I have two CPUs. So in the CPU, what I do is I first say I need a flag in my memory, so let's call this location at the top. This was going to be called gatekeeper in this instance. So the first location is a gatekeeper, and then I have my two CPUs, and in my CPU I've got register 1, and I give it the value of 1. In my second CPU I have the exact same situation. I have register 1 with a value of 1. And then I perform this swap operation, and the swap is the atomic test and set operation. So what does it do? Well, my gatekeeper has a 0. In one operation, I go, is that a 0? If it is a 0, then I'm going to swap this. This is going to be the 0, this is going to be the 1. Right? So then you can say, well, if R1 has a value of 0, so you branch if not 0. So if it has a value of 0, then you know that you've gotten the flag. If you've got the flag, then you can carry on. In the meantime, your second CPU tries the same compare and swap. What it's going to get is it's going to swap a 1 for a 1, it's going to see a 1. So it's not going to have updated the flag, and then it's going to say, well, what do I do? Well, I loop around this loop and keep on testing. So CPU2 just keeps on testing, waiting until you finally got the 1. Until your first CPU says, okay, I've finished writing to memory and updated my gatekeeper back to have a value of 0, which is what happens in the final two operations. For anyone just wanting to read the syntax in ARM, putting the memory location into a register, putting a value of 1 into a register, swapping register 1 with the address pointed to by R0, so that's the address of gatekeeper, swap those two values and store it in register 1, branch if you get a 0, and then just return the data. So it should be quite straightforward to see how this works. And this kind of brings us on to the idea of critical regions, where we have a section of code that we don't want it to not be interrupted by a process, so we have these kind of operations to support this. And the main examples will be writing shared memory, which we've talked about a lot, or accessing some I/O. I/O might want to write direct to memory. It can be the same kind of issue. It also allows you to pass messages, but we'll talk about this next. So we're going to change to a different set of notes. The reason for this is that the primary set of notes is tied to this textbook. Right, so the second set of notes, giving an example of, this is the typical example of mutual exclusion, or why it can be a problem. So this is exactly what I've talked about already several times before. I've just written it in some kind of pseudo C-ish code. So I have two tasks, and they're both accessing some same shared variable, which is a global variable in memory. What can happen? Well, the first task, it stores the shared variable to a temporary variable. Then it's going to perform some function which updates this temporary variable, and then once it's done this update, then it writes it back to memory, to the global variable. Task 2 does exactly the same thing. So, how can I get a problem with this code? Yeah, so imagine what happens if at this point here I get a context switch. Or rather, any point during this update function I get a context switch. Then you can be reading the wrong variable here, or overwrite something. So well, you get a context switch here. This process completes completely, then this process continues to run. What gets lost is this update in task 2, right? Because this value, which is written once, it gets immediately overwritten in my first task. That's your classical example. It's worth considering that it can happen at a much finer level because it can happen at any time. So imagine I've got this simple code with 2 processes. The first one is just C. All I do is increment a variable. And the second one, I decrement a variable. So, can anyone suggest how I could have a problem here? One operation, incrementing and decrementing. Say I'll run process 1 and 2 at exactly the same time. How could I go wrong? Yeah, so I get, one increments, one decrements, but actually that's what I want it to happen. First one increments, the second one decrements. I want my result to be the same as it started off to be. Why? How could it be the case that my result, after both processes run, the result is either one higher or one lower? Yeah, exactly. This is C code. C code is not what runs on a machine, right? You actually run assembly code. So now that I'm running assembly code, you can see exactly how this happens. You first load a value from memory, you increment the value, then you perform the context switch. This code runs, I write my value to memory, and then I just overwrite the value. You can follow this in a bit slower. So imagine I had an initial value as my shared variable of a value of 10. The first thing I do is in process 1, I increment this value. So first I copy the value from shared memory into my local register. Then my local register stores value 10. I increment it, this operation, so it becomes 11. Then I do a context switch. My second process, well, it goes, okay, I'm storing the value of 10. I decrement it. Then I update the memory. So now my memory has a value of 9. Then what happens, this process finishes, it goes out, the first one comes back in, it continues on, and it loads the value of 11 into memory. And what you can see is this operation here has been lost, and I've actually incremented my value when I don't want it to. So that walks through it again. So let's talk a bit more about solving the problem with semaphores. So, semaphores. What are semaphores? They're a primitive to allow me to control my critical regions and control multiple processes, communicate between processes. All very useful. So what is a semaphore? I've brought an example of what a semaphore is. Are you excited? Yes. A semaphore is this, a water bottle. A semaphore is a talking stick. If I've got the bottle, I can talk. It's as simple as that. So you've got simple processes, you've got access. What you have to do is if you have it, you can talk. If you don't have it, you have to wait. So the first thing to do is you say, operating system, can I have it? And if it's available, it'll give it to you. If it doesn't, it won't. Then you perform your operations, and then once you've done, you give it back to the operating system. Otherwise, everyone else is waiting forever. And so that's called a signal, or in microCOS2, you have, it's called OSM post. We'll go into the syntax in more detail. But it's really that simple. It's just a simple, whoever has the talking stick can talk. Bit more detail, well actually, a semaphore can actually have a counter. What does this mean? Well, the semaphore is no longer my water bottle. The semaphore is now my bag. So what can you do? Well, I want to talk. I can take out a water bottle. Someone else wants to talk. You can take out a water bottle. Now we can both talk. No one else can talk. Someone else wants to talk. Sorry. He can't talk. So he's joined the queue of blocked processes. Right. So the operating system will, in this, the semaphore will keep track of everyone who's blocked. And then once this guy's finished, what he's going to do is he's going to return the semaphore to the operating system. And the operating system is going to give it to the next guy. And I'm glad I took two people who can catch. Right. So this is all we do. And yeah, so you wait on a counter. Every time, how you actually do it in a computer, you don't have blocks, you have a counter. You initialize the counter to how many processes can share your variable. So why would you want more than one process having access? It doesn't need to be a shared memory location. It could be, say, I've got 3 printers available. So the first 3 people can grab a separate printer, and you can use a single semaphore to control it, because as a process you just say, can I have a printer? You don't want to say, I want the first printer. So you can have multiple processes, they all wait on this counter. As you fill it up, you fill out the processes, your counter becomes 0. So that's straightforward. If the queue is empty, the counter increments. So once I've finished using all my tasks, finished working with this in the critical section, I can return the semaphore. So then the counter will increment. Of course, if there's something on the blocked processes, what's going to happen? I return it, the operating system immediately gives it to the next one. So the counter doesn't actually change, it passes to the next highest priority task. Right, so this is all rather straightforward. There's an analogy with basically my water bottle analogy here. So how can we use it for signaling? So yeah, we've talked about it's going to be key for critical sections. Whoever has the semaphore has access to a critical section. How can it be used for signaling? Well, basically, the second you're done, you put a semaphore, you say, here's the water bottle. I've finished my task, and this guy can come and grab the water bottle. He's just waiting for me to return it. That's a simple, I'm finished. And for more complex data transfer, you might have a more complex signaling back and forth. Right, so that's all good and fun. Back to the syntax for semaphores, because you're going to be writing several of these guys. Okay, first off, what we have to define is this is actually the semaphore for the operating system. So I'm having a pointer to this OS event thing, which is my semaphore. Why is it a pointer? Well, because it's not just the counter value, it also holds the queue of blocked processes. So that's what's held in this OS event thing. We have some variable which allows us to check the error properties whenever we assign a semaphore or rating on it. Not as critical as other checks. Note that in these cases, when you declare a semaphore, it has to be a global variable, because multiple tasks are all going to share or try to access the same semaphore. Okay, so then you get to your first task, and what you have to do is you have to initialize the semaphore. And that's this sem create, where the 1 is your initial counter value. So I have a semaphore with just one process that can touch it at any point in time. So this is what you'll typically use for shared memory. Then we've got the pend and post. So this is wait for the semaphore. This is signal I'm finished with my semaphore. Again, just syntax OSM pend. This is the name of the semaphore that you're waiting on. So this is the name. Next bit here, this is actually a timeout. So you can actually use semaphores to say, wait for this guy to finish, and if he never finishes, just give up. So that's useful, but we won't be making too much of a use of that. And if you have multiple processes, they have the exact same code. So the second code, when it asks for a semaphore, it's going to ask for the exact same thing as the first process. And it's going to post in the same way. So you can imagine these two processes, this one and this one, are competing for the same semaphore, or competing for what will be a shared memory location or something. Okay, because it's a bit ugly to write so much code, you can use this macro, so it's defined in the microcs2 environment. What does this do? So I can, instead of writing os sempen protect sem blah 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 blah, I can just write cs brackets x. So where x is the code I want to run, everything else around it is, so this says put all of this code, all of OSM pend and OSM post before and after x when it compiles it, so the compiler can actually read the full code. And it just allows us to simplify it. So you still have to declare it, and you still have to initialize it if you use this macro, but you can simplify what you do in your critical sections to just have the CS. So, simple example time, and then complex example time. Simple example. This is really just highlighting how this could actually happen in practice, how you could go wrong. So, in this example, I've got two tasks. I'm defining this is version 1, and what I'm actually doing in version 1 is I'm removing the critical section. So I'm saying, get rid of the macro in this code. So CS actually does nothing. Okay, so CS does nothing. What happens? So I run my start task, and my first task, what it does is it creates a secondary task, and then it's going to run for 100 cycles, and it's going to take a variable, read a shared variable, increment it, and then it's going to go to sleep till the next tick. So when it goes to sleep till the next tick, what's going to happen is, well, task 1 is going to wake up because it's it's the only other task available. The next highest priority task. What does task 1 do? Well, task 1, it reads the shared variable, increments it, and then writes it to memory. Then again, reads the shared variable, decrements it, writes it to shared memory. Right? Now this process runs forever, right? There's no OS time delay. So will this just increment and decrement a variable forever? Can anyone say why it won't? No? Yeah, the start task. The start task is actually a higher priority task. So after the timer tick, it wakes up and then it can continue on its own code. So its own code is it's going to then write the value to memory, and then it's going to decrement a value, wait a second, write the value to memory. So it's just two processes are both incrementing and decrementing a value. It's not too exciting. But the idea is that if you're only incrementing and decrementing a value, then the range of your variable should be either 0 or 1 at any point of time. So what actually happens if we run this? It's rather slow. It works beautifully to defy me. We can see that after however many clock ticks, it's going away from what we expect. It's going out of the range 0 and 1. So why is that? Yeah, exactly. So because we context switch it within our start task, um, we don't know when we're going to be incrementing and decrementing in the other task. Right, so what happens if I enable my critical section? Now obviously you all know that this is going to solve my problem. The question is, what actually happens? Why would it solve my problem? So if I enter my critical section, so this is now a critical section, it's protected by a semaphore. So I do temp is equal to shared int, increment temp, and then I break out of I give the operating system, it says, okay, run another task. Right? So the second task runs. What does the second task do? Second task 2, it starts and it says, straight away it reaches the critical section. Because it's reached a critical section, what does it do? Yeah. It can't do anything, it waits. So it's just going to wait. Then my primary task at the clock tick, it's going to wake up, update my shared variable. And then you could imagine, because of that, my shared variable is always going to stay in the range 0 and 1. Okay, now looking at this code, what you might think is a bit odd is, why on earth are you context switching in the middle of a critical section? Right? It's kind of asking for trouble. So, I created a second example, which is a lot more flaky. But this example doesn't have a context switch in the middle of a task. This one's going to take a little bit longer to walk through, and I'm going to ask you all to think a bit more about this. So, this process has 3 tasks. Task 1, task 2, task 3. Task 1 takes a shared variable, increments it, and then writes it to the shared memory. There's no semaphores, no protection, no critical sections. After it does that, then it goes to sleep for 2 ticks. Right. Task 2. Task 2 reads a value from shared memory, and this one actually takes some time. So it's more like it does some procedure, using the value from shared memory, does some work with it, and within this code, I tell you that it returns a value in the range 10 plus 1 to 10 plus 5. So increments the value of 10 between 1 and 5. And it's some random function, but it takes some time to do this. Then you write that back to your shared memory. Okay. Task 3 does completely unrelated work. It doesn't touch the shared variable at all. Okay. So to summarize, task 1 increments by 1. Task 2 increments by between 1 and 5. Task 3 does absolutely nothing at all. So, what do you expect to happen to my shared variable? So my start task, it does nothing else. All it does is it prints out my shared variable over time. So what should happen with this shared variable if I've got one task incrementing it and another task incrementing it? Hope you should imagine that if you're incrementing it, then it should always go up. Yeah? So we can check that it actually does this. So initially, what I've done is I've said, okay, let's say there's no task 3. There's just the 2 incrementers. Wait for it to come. So who thinks it's going to just increment? Can we have a vote while we're waiting? Who thinks it's just going to increment? It's always going to go up. But 4 people think it's always going to go up. Now it's very hard to see because it's lightning quick, but it always goes up. 4 people are right. The rest of the class is wrong. Right. Now I'm going to implement task 3. And who thinks now that it's going to continue to go up? 1 guy, 2 guys, 5 guys. We're more confident that it's still just going to increase. Tension. Can you feel it? Right. Unfortunately, it has just gone up. Is it? Right, this is what happens when you test something at home and just in a lecture. Regardless, you can play with this on your own computer and perhaps try implementing more tasks and see if it... I'm going to tell you that in some cases, it doesn't always increment. And just by adding an extra task which does completely unrelated work. So, assuming that it does this, speak to your neighbors. I'll give you 2 minutes and we can discuss. Someone will come up with a solution. So, 2 minutes. Go. Right. Someone asked an important question about priorities. So you'll never be able to answer it without this question. So task 1 is higher priority than task 2, and task 3 is the highest priority. So task 3 is the highest priority, then it's task 1, then task 2. Right. And by the way, as you can see in this example, we have got it incrementing and then decrementing from 5 to 2. So it does go wrong. So, another minute to work it out between you guys. Okay, does anyone have an answer? Does anyone have an answer? Two people have an answer. Let's go.
I reckon that they're using the same registers, and so even though the memory value isn't changing, you'll have like one thing which is you'll have like one task changing the register value, and it's about to change that to memory. But then task where it comes in and tries to change the register value instead.
Not quite. It's close, but it's not quite.
So when you basically, if this task three is a high priority one, when task three is up, so that task one and two get a chance to run. Task one will run first, and then do its A1 thing, and then they'll let task controller task two when it gets a chance. But then because task three is a new one, it's high priority. When it jumps back in whenever it wants, and then it'll basically the task two can't finish running. And then the next time task two comes up again and go back to task one, which can lead to task one reading the value, and then task two writing in and then whenever it goes to task one from the task three, it's left with the lower value that's read it previously.
So who got that? Yeah? Right. That is basically spot on. Right. So what you have is you have multiple timer ticks. Right. So say there's no task 3. What happens is that I've got task 1. Task 1 takes a certain amount of time and it runs task 1. Once task 1's done, then task 2 runs. Okay. Then what happens? Well, I probably should have pointed this out, but so task 1 goes to sleep for 2 ticks, task 2 goes to sleep for 1 tick. So, to my drawing, after task 1's going to wake up 2 ticks later, task 2 is going to wake up 1 tick later. So that's what's going to happen if I look at my process over time. So let's look at my shared variable. So I've got, imagine my variable was initially equal to 0. Task 1, at the end of task 1, my variable is going to be incremented to 1. Task 2 is then going to read 1. Right? At the end of task 2, it's going to add, say, 5. So then I have a value of 6. Then it does nothing. I start again. I read a value of 6. I add, say, 3. So then my shared variable has a value of 9. And then I continue the next tick. Okay, it reads in a value of 9, writes out a value of 10. So I write a value of 10. This one reads in a value of 10, writes out a value of, say, 11. And you can imagine with just 2 processes, because there's enough time for them to complete, you don't have any issues, and there's no preempting. So what happens when I have a higher priority task? Start again. So I've got 3 ticks again. Right, so task 3 is now the highest priority. So task 3 runs first and it occupies a lot of this time. Right? Then task 1 runs, and then task 2 starts. At this point in time, task 3 runs again. Task 3 runs, finishes, task 2 runs for a bit longer, but it's not quite finished yet. Then task 3 runs again at the next tick. Then I run task 1. So I should say this is task 2, task 1, and then task 2 is going to say finish. So task 2 finally finishes before they get my next hot tick. Okay, so what is my value of my shared variable? My shared variable is, well, it's initially 0. So it says 0 until it gets incremented by task 1. At this point it becomes 1. And task 2 reads in 1. Then it carries on, and in this whole tick, nothing happens, because task 3 takes up most of the time. Task 2 takes up some time, but it doesn't update the shared memory. Okay, when does it finally change? Well, okay, I read in a 1, and I increment that to a 2, and then say that task 2 randomly chose to increment it by a value of 1. Task 2 initially read in 1, it's going to read in 1 at this point. It's not going to read in anything, and it's going to write in to 2. You can imagine that task 2 in this case hasn't actually added anything, right? Because I've got a 2 before task 2 and a 2 just after task 2. So whatever task 2 has done, it hasn't actually achieved anything. You can imagine if you carry on this a lot more cycles, then you can actually have it looking like a decrement, because task 1 keeps on incrementing it, and then finally task 2 increments it, but it increments it less than what you previously had. Right, so how can we solve this problem? Get rid of task 3. Task 3 is high priority. It's crucial, despite the fact that it does nothing. What can we do to solve this problem? Yeah, so we can use the semaphore, or so in this case, because we only have one critical variable, whenever we want to access it, we would have to write a critical section. So, looking at task 1, you'd have to write a critical section from when it reads the variable to when it finally writes it. When in task 2, you'd have to do the same. So you would critical section all around this procedure, including the one that takes time. So if I was to look at my diagram, what's going to change? So I've put critical sections on this timing diagram. What here is going to change? Anyone? T3 will come back in, because T3 is not waiting on semaphore, so it can just, it's the most high priority, so it's always going to come back. This T1 won't happen. So at this point, T1 grabs a semaphore here, it releases a semaphore. T2 grabs a semaphore here, it still holds the semaphore, so T1 can't start. So instead, this T1 isn't going to run, T2 will finish, T2 will finish, and then T1 will run. And then T1 at this point is going to be reading the correct value. Right. I think that's probably a good point to stop. I do recommend that you have a play, put the critical section in this code yourself, and get it working, and that'll help you understand it a lot better.